Alright, so let's talk about energy conservation, including rotational kinetic energy. I have an example question set up, so let's use this example question to discuss rotational kinetic energy. So where does that come from? Well, we have these two boxes. This is an Atwood machine, right? M1, M2, and in this example, M1 has 17.5 mass, and the M2 is 12.5, so M1 comes down and M2 goes up. That was before rotational kinetic energy. And now with rotational kinetic energy, this pulley is considered a disk, and it has a rotational inertia that's given right here, rotational inertia of that pulley, and also has a radius. So now when this thing starts spinning, it should have some rotational kinetic energy. So how much is rotational kinetic energy? Well, let's say K rotational is, according to our comparison with translational, 1/2 mv squared, right? So mass gets replaced by rotational inertia, and linear velocity replaced by angular velocity. So this is rotational inertia of an object rotating around an axis, and this is that corresponding rotational inertia, right, around that axis, and you multiply it by the speed, divide by 2, you get rotational kinetic energy. Okay, so now we have these objects. So 1, 2, and maybe I would just put a 3 here. So these three objects potentially have energy, and let's name this a Roman numeral 1. And then when 1 comes down and about to hit the ground, Roman numeral 2. So at this point in time, we can sum up the energies. And this point in time, we sum up the energies, and then we equate them. The question is, when bucket 1 reaches the ground, how fast it is traveling, and bucket 2 should be traveling at the same speed. And we're also assuming that there's no slipping between the rope and the pulley. So the pulley will rotate as fast as the rope passes through it. So the linear energy, the linear velocity at the rim of the pulley matches that of the rope. So if the rope is slipping, for example, then the linear velocity of the rope will be exceeding the linear velocity of the rim of that pulley, right? Or the other way around, if the pulley is spinning, but in this case, the pulley is passively rotating with the rope's influence, so that wouldn't happen when the pulley somehow can be faster, right? So now let's discuss the mechanical energy at point 1 in time. So this is point 1 in time. So we have energy of the first bucket, energy of the second bucket, and energy of the pulley. I think I numbered it 3. So there are 3 of these, and I'll list all the generic terms. 1/2 mv squared. These are the bucket 1, 1/2 m2 v2 squared, bucket 2, and also 1/2 I, that is 3, but we only have 1 rotational inertia, and that would also be 3, but we only have 1 object rotating anyway. So these are the kinetic energies, and then we also have potential energies. So m1 gy1 plus m2 gy2. We can set up a coordinate that points upward. So this is my y-axis. The ground level is 0. So by using this formula, I can find my total energy. So let's see. The masses are given and the height is given. So 2.2, and the other one is 0.8. So this location here, 2.2, and this location here is 0.8. Okay. So let's see, if N1, bucket 1 comes down 2.2, and then bucket 2 has to go up 2.2, right? So in this diagram, that distance here should be at 0.8 plus 2.2, so 3.0 meters high. That's how high the bucket 2 has been pulled. So that's also a 3 for the pulley. Okay, so now let's calculate total mechanical energy at point 1. This is going to be 0. We're releasing both buckets from rest. That's 0. Rotation also 0. And then each one of them has an initial height, so initial potential energy due to gravity. So the first bucket is 17.5 kilograms times 9.8 times its height 2.2. And the second bucket is 12.5 kilograms times 9.8 times 0.8. Okay, so you can find out the total mechanical energy contained at this point in time. So go ahead and pause here and use your calculator. Okay, we're back. We have 475 joules. Alright, so now let's calculate total mechanical energy at 2. So we have the same terms, same generic layout, and let's make this assumption: the buckets are moving at the same speed because the rope does not stretch, right? So we'll put them over here. V1 equals V2, and we're also making an assumption that the rope is not slipping over the pulley. So either V1 or 2 is going to be equal to omega, angular velocity of the pulley, times the radius of the pulley. So let's say this is equal to that and equal to v, so they have a common velocity. Okay, so moving down here, now we have all these three terms are going to be non-zero. Starting with the first one, 1/2 m1v squared. Then second term, 1/2 m2v squared. Third term, 1/2. This I is given 0.05, right? So I times omega is v over r, right? So omega v over r. And this is v squared over r squared. Plus, now m1 has dropped to the ground level, so this is a 0. No height. m2 has been pulled up to 3 meters. So m2 times g 9.8 times 3.0. I think we can just replace m2 by its quantity 12.5. Okay, so we have this, and let's combine some terms. V squared, right? V squared, v squared. So we factor out v squared. Now we have 1/2 m1 plus 1/2 m2 plus I, rotational inertia of the pulley, over 2r squared, the radius of the pulley, plus this quantity here, 368. Okay, so let's plug in more numbers. V squared, so mass 1, 17, so 0.5 times 17.5 plus 0.5 times 12.5. So I can factor out 0.5 plus 0.05 rotational inertia, 2 times 0.12 squared. Okay, so plus 368. And use your calculator to calculate that. We get 16.7 v squared plus 368. And using energy conservation, E1 equals E2. So we have 475 equals this. Right. So we have v squared equals 475 minus 368 over 16.7. And you can use your calculator. I'll fill in the numbers in a second. So we have 6.41. If you take a square root, and it's approximately 2.54 meters per second. Okay, so what changed? Well, what changed was there was an additional term here. So this term was not there with our past energy conservation calculations. It was just these and those. So the result is you start with the same exact energy as you had before, ignoring the rotational kinetic energy, and then the speed actually is supposed to be a little less if you do not ignore the rotational energy in your calculation, because part of that total is going to go into this at the end of the bucket once traveled down the vertical direction, right? So some of that energy is going into spinning the pulley. So the rest of the parts will have slightly less total energy, so they'll be moving slightly less in speed.